right. Good morning. So you probably saw I posted the grades for midterms. I think you probably would have seen most of them already. What I've done is taken a kind of an estimate for your participation so far and average to the scores that we do have according to the weighting that we will have on the syllabus. But of course, right now we don't have all the grades in, so this is just averaging with one exam score, not three different exam scores, right? So there's several aspects of that grade that are not fully reflective of what you ought to expect. But hopefully it's useful, and at least the grades are up, and you can see that. You'll also notice in Moodle that I just fill in, so I have my own spreadsheet where I do the calculations. I'm not relying on Moodle to make the calculations. So I track everything on my spreadsheet, and then I just force it to say, okay, anything in this course total category is your total grade. And I'm just doing that in my Excel sheet so I don't mess anything up in Moodle, and then bad things happen. Okay, another thing, I should probably have a little announcement page. Maybe I'll do that next time. I was mentioning to a couple of you that I overheard you talking about CI courses, communications intensive. As you're scheduling for courses next semester, I'll be teaching a course called Water and Wastewater Treatment in Developing Countries. And as part of that, I'm hoping to bring students to Nicaragua as a study abroad for the spring break. So if any of that's interesting to you, it's $41.56. The trip would be optional, and the idea is that it's going to be somewhat of a service, fieldwork, volunteers sort of a thing with a nonprofit that works down there for development, water projects, and so they do water sanitation, and then all sorts of other things, agriculture, microfinance loans, things like that. So it would be a pretty neat trip. I think things are looking good for it. I went to visit in March this year, so getting some good things going there. So let me know if you have questions about that. I think you'll probably see some sort of an announcement in the next week or two in terms of what that requires in terms of like a study abroad application and things like that. So stay tuned for that, and also consider that if you're interested. Overall, that trip, my aim is to make it as affordable as possible. I can't really do anything about the cost of flying there, but except that I'm able to cover my own expenses through my through grant. So in terms of study abroad expenses, it's like approximately $400 or $500 plus a plane ticket for a week. So it's probably going to be one of the more affordable options. Okay, so today we're going to get into hardness and water softening. So hardness and alkalinity, understanding those so that we can talk about how to treat them as a water issue. I'm skipping a little bit of kind of the last segment. We left off on UV treatment for disinfection, and I had thought about doing a little bit more depth on either UV or advanced oxidation processes, but I want to get to this segment, the softening segment, before I revisit that if I do, because the rest of what I had to say there was more like a research highlight kind of a thing, and I wanted to make sure to give us time for the hardness and softening as kind of the core skills that we need for our next exam, and to cover that and have plenty of time. So I think we're making pretty good progress in general, even though we're going to have one class missed again Thursday next week. Okay, so we saw this graph earlier in the semester when I was kind of introducing different topics that we're going to cover. Hardness is essentially the mineral content in water. Now, that's an overgeneralization. It's not just any mineral, it's the type of minerals that, well, A, that are common, but B, that have certain properties that they are contain multivalent cations. So sodium would not count. It's just got +1. So multivalent meaning like multiple charges. So calcium with a 2+ would count. And then if we had some random weird rare earth metal that just there was 1 nanomole of it in our solution, we would never even notice. So we're not going to include that either. Right. So things like that. It's a mineral, sure, but it's not anything meaningful in terms of our water quality. So hardness then is approximately the amount of calcium and magnesium. Those are the two major ones. So Ca2+ and magnesium 2+. They are very common. They're kind of everywhere. Of course, there's some, if we were to dissolve something, it'd be maybe magnesium sulfate or calcium chloride or something. There's some other component to it, but we're going to measure things in terms of typically, and you'll see this up here and we'll talk more about it, as calcium carbonate, CaCO3. In terms of, let's imagine that all of this hardness was there by adding calcium carbonate. You'll notice when we get there, that turns out to make the math very convenient to work with to do that equivalence calculation. Okay, so if we're measuring it in that manner, it's kind of I guess I'm misspeaking a tiny bit. This we see over here on the right, milligrams per liter as CaCO3. That's what I was referring to. Another way we can do it is milliequivalence, and this is going to be charge. So if we want to do it in terms of a charge balance type of circumstance, we'll see it can make sense that way. But a little more often or a little more tangibly, we'll talk about it in milligrams per liter of calcium carbonate. So how much of this stuff would we have to dissolve to get the same hardness? So if we look at the map with that in mind, anything that is up at 300 or so milligrams per liter as CaCO3 is very hard. That's everything in red over here, basically. Well, that's 180 plus. We would consider this 120 to 180 range, or maybe somewhere around there. I guess this table doesn't match the chart exactly. 150 to 300, we would call that hard water. And that's going to be water that you'll notice that anytime you are using, let's say you rent an apartment for a little while, within a couple months you're going to start seeing mineral deposits around your sink, kind of thing. Very hard water, that would probably be happening within a few weeks. And you're going to notice tangibly with hard water, if normally like you put some soap on your hand and add some water and you're like swishing it around to make suds, with very hard water, it's going to be really hard to actually get those suds. You're going to need a lot of soap, and it's going to take a little more effort to actually get to the point where you have the soap suds. Effectively, the amount of charge in the solution is impacting how the soap is acting, the soap molecules act. So we can go up and continue. Moderately hard is you probably wouldn't notice it very much. Maybe mineral deposits over time. And soft water, I think we're probably somewhere between soft and that moderately hard, if I were to guess. And if we take a look here, somewhere in there, yeah, it's probably soft unless we go down to New Orleans or something. But even that, I'm not sure if this is referring to the water supply or the actual just groundwater. So that's a little vague, but okay. So soft water, you might notice if you get really, really soft water and you're not used to anything near that, when you try to wash soap off of you, it'll feel like it never comes off. You'll have kind of this, it feels like there's a layer there, and it just feels sort of weird. That also has to do with some of the particle interactions. Specifically, if you recall, we talked about coagulation. We talked about that electrical double layer. So really soft water means that that electrical double layer goes out a pretty far ways. So it's actually hard for things to touch a surface, particles and things. And that same dynamic happens with soap. And so it kind of, with that extended double layer, it feels like you're not getting the soap off because it's changing that interaction there. Okay, so to dive into alkalinity and hardness, one of the key features here is the carbonate system we need to understand. We already talked about calcium carbonate, so CaCO3. There's some hardness there from the calcium, but this is also an agent that's adding what we will call alkalinity. Now, alkalinity, I should have defined this already, is essentially, we could call it acid neutralization capacity. And I think I do have slides on this. So we'll come back to this. What I want to note here is that if we add calcium carbonate to some system, and then we recognize that the carbonate system has this equilibrium chemistry with pH, if we were to add calcium carbonate, then each of those CO32 minus, CO32 minus, each of those could take 2 protons before they became H2CO3. So effectively, we're adding something that was probably going to take a proton, or is happy to, at a neutral pH. We'll take a look at this graph in a moment. That means that it's happy to consume some of the acid. And in fact, calcium carbonate, the carbonate in that, could consume enough acid to become CO2 and then leave the system. So it could literally take away the acidity by then leaving as CO2 if the charge balance of the solution could accommodate. So that's kind of interesting that we see that there's that neutralization capacity built in, and that's due to the carbonate system. So the carbonate system here, if we dissolve CO2, or if we add it as CO3 minus, any way we put in CO2 of some sort, we end up having equilibrium. We talked about this with the chlorine system. We have equilibrium between carbonic acid, H2CO3, the bicarbonate, which is HCO3 minus, and carbonate, which is CO32 minus. So we've got this equilibrium acid-base system, and we also could note that CO2 dissolved as an aqueous CO2 will be in equilibrium, we'll say plus water, essentially is the same thing as saying H2CO3, because it's the CO2 adding 1 oxygen and 2 hydrogens, that gives us H2CO3. So that'll be in equilibrium, and then all of the following down here will be in equilibrium. So if we take a look at relevant, like normal pHs that we might deal with, here would be neutral. Most of our carbonate is going to be in this form, because this graph here is a log of the portion of that particular species. So there is some of this guy, log to the -1 here. That should be about 10 times less than there is of this one. And if we take a look, this one here should be the H2CO3. And yeah, that's right here. Right? They are actually defining the alpha for each of these lines. This is the fraction. So the fraction that is H2CO3 compared to the total carbonate in the system. So we actually did these fraction type analysis when we talked about the chlorine system. We said, okay, well, what portion of the chlorine is in HOCl form, right? We were actually solving for this type of fraction. So in this case then, maybe 10% is H2CO3 and 90% is HCO3 minus, the bicarbonate. So we could take a look at that, and we can see pretty easily with this graph at what pH do we have the different species, and how much of them are we going to expect. So if we take, for example, very basic conditions, we expect almost everything to be in carbonate form. Very acidic, we get the H2CO3. You might recall that the stuff in your Coke or soda of some sort is basically going to be CO2 dissolved. And you might also know, or if you ever take a look at the bottle, there's probably phosphoric acid in there. And that's added to acidify it and to keep the carbonate in the bubbly form, right? The form that can degas as bubbles, right? And so as soon as you change the temperature, or if you were to change something about the system or give it some ability to degas, drop a Mentos in there or something, you might have some rapid exchange of the gas, right? When you drink it, unless it's flat, unless you've lost all the carbonate, then ideally it's bubbly and interesting, right? That's kind of the system there. Okay, so this is the carbonate system. This stuff is going to use the same equilibrium chemistry that we've talked about previously, noting that at any one of these lines we would take a look at equilibrium from one to the other. So we'd have two different reactions, well, three if you include this guy. We'd have one for H2CO3 in equilibrium with HCO3 minus and a proton. And we'd have one for HCO3 minus and carbonate, CO3 2 minus, and a proton. Okay, so we end up with these two primary equilibrium reactions, each with their own pKa, which we could find here, right? Here's pKa 2 and pKa 1. And we could define the system that way, right? So we can understand the carbonate system pretty well. All right. So this is basically an elaboration of just that. So we have CO2 aqueous with water. That gives us H2CO3. That then is in equilibrium with bicarbonate, which is then in equilibrium with our carbonate. Okay, so now in the case that we have calcium carbonate, that's just adding straight CO3 2 minus. And that's actually pretty common if we ever have minerals that, anything like lime, anything that had influence geologically from some sort of oceanic deposits. We've got a lot of diatoms and things in the oceans that will form calcium carbonate shells and then sediment out over time, and that forms essentially minerals that on geologic timescales would then move around and then be source minerals for systems elsewhere. So there's a lot of that in our natural systems, so we can expect that's going to be that would happen. Okay, so then let's see, this page, it just kind of goes on to describe the way we can describe the K1, K2. And this last one, we talked about these equilibrium reactions before. I didn't really elaborate on precipitation and solubility reactions, but they're essentially the same thing. So I'm just going to take a moment to highlight this at the bottom here. For solubility products or solubility reactions, they are also just the same type. They're equilibrium reactions. The only thing to keep in mind is that the solid phase, assuming we have some solid phase like water in a swimming pool, there's the pool lining, let's say it's a mineral, there's still gonna be some of there, even if a little bit of it dissolves, right? That's the expectation. If water is flowing over rocks in a stream, the rocks don't completely dissolve, but a tiny portion of them do, right? There's that aspect of them. As long as there is a solid, we have to consider that solid as unity in our equation. So the concentration of any solid equals 1. I'm just going to put X there. So whatever solid we have, we're going to treat that as a concentration of 1. So if we take a look at our calcium carbonate, we would say if we had calcium carbonate solid in equilibrium with calcium and carbonate, then when we do our solubility product, we'll say this is going to be equal to that calcium times the carbonate divided by this solid, which is just going to be 1. I'll write it out. Okay, so that's just a thing to keep in mind if we're doing a solubility product. Okay, and you can see there are values given here for each of those. All right. So another thing, this is kind of the approach that we took when we were solving for what portion of something is in the HOCl or is in one form or the other. This is kind of an elaboration of that process. So if that was at all confusing, this is probably a good spot to take a look. And really, I'm just taking from our book and just putting it here for us to have kind of step by step through it. So I'll review it really quick. Whenever we are looking for maybe some fraction, the fraction that is, let's say, HCO3 minus. The fraction, that would be that over the total, which would be H2CO3 plus HCO3 minus plus CO3 2 minus. Okay, so if that's our fraction, then sometimes it's helpful to just take a portion of it in some case and say, well, at a high pH, we can actually ignore the contribution of the stuff that's not going to be there hardly at all, right? At a high pH, we don't expect any H2CO3 to be meaningful. So if you look at this diagram, we were just looking at the same one. If we were up at pH 12, the fraction that is H2CO3 is 10 to the minus 7 or less, right? So it's so completely meaningless for our calculation that at some particular pH, we can ignore them. So at some conditions, we could maybe ignore this guy or maybe ignore this guy, depending on the scenario. So that can help us simplify one of these equations. So the book is noting here that unless the pH is extremely high, it's usually carbonate that we ignore. And if we look here at anything, so this is pH 8 right here, carbonate is already 1/1000th of the solution. So anywhere at a regular to slightly acidic pH, we're kind of just ignoring carbonate. And if we're not ignoring carbonate, then chances are we can ignore the carbonic acid, the H2CO3. So that can help us simplify our equation, and then it becomes much more like what we did with the chlorine, and we can simplify by dividing the top and the bottom and get some ratio. If we can get some ratio in terms of K and H plus, that becomes quite convenient. We substitute in, so we have two different equations, right? We have the fraction that is, in this case, bicarbonate, and we have a the equilibrium equation that we can rearrange to have that proportion that we can substitute in, and ultimately get this fraction in terms of just K and H plus. Okay, so that's kind of where that analysis is heading. This is just kind of elaborating on just that. Okay, does that make sense? All right. Okay, so I want to take a moment to talk about open versus closed systems. When we're talking about natural water, typically we are open to the atmosphere, so there's free exchange of CO2. But certainly if you had the Coke bottle example, you have a closed system, at least until you open it and the bubbles go everywhere, right? So that's going to be important for us to consider what we're speaking about when we're dealing with the carbonate system. If we have some sort of a closed system, maybe that gives us an easier time of understanding what's happening inside of it, given that there's no exchange. But in reality, we have Henry's law that will dictate how much gas exchange we have between the atmosphere and whatever solution we have. So, for example, my water bottle here, it is closed, but there's enough atmosphere in here that there's pretty much free exchange for a little while. So unless I were to have filled that headspace with some different gas, which I didn't, then it should be pretty normal, acting as if it's like open to the atmosphere, right? So, but if we had sealed that completely, or maybe put some sort of inert gas in the headspace, that might change things. Even then, I guess if there was CO2 inside the bottle and gas space, headspace for it to leave to, that would still be in some way open. Okay, so at any rate, one of the things we can do if we know the CO2 concentration in the atmosphere, which we can pretty easily know, we can then solve for how much we expect, how much CO2, how much carbonate we expect to be in the system based on that exchange, if there's no other factors. So there's an interesting problem here, and this is again from our book. So the CO2 data is a little outdated. I think we're up around 410 now or so, parts per million CO2. But we'll use their values here. It says estimate the pH of natural rainwater, assuming that the only substance affecting it is the absorption of CO2 from the atmosphere. And it says assume that the concentration of CO2 is 390 parts per billion by volume. The temperature and pressure are 25 Celsius and 1 atmosphere. Okay, so we don't have quite everything we need for this just yet, so but I think it'll be well worthwhile to walk through it together. I've got the solutions here that we can look at, but take a minute and think about what it would take to solve that problem. What would you need and how would you approach it? first part would probably be to take a step back and say, well, what about this Henry's law thing, right? How do we incorporate Henry's law? We need some value for that for the CO2. So if we take a step back here a moment and say, okay, well, Henry's law says we have some concentration of gas, and this is going to be gas that has dissolved, and we see the brackets, so that should be moles per liter, is going to be equal to Henry's constant with moles per liter times atmosphere units, or per atmosphere, and then the partial pressure of that gas in ATM, atmospheres. So when we take a look here, we could say we want to know the CO2 concentration dissolved. That's going to be equal to some Henry's law constant that we'd have to look up given the temperature, and that should be something we could find, times the partial pressure of CO2, right? That was basically it, right? And so the partial pressure, if you recall, should be, if we have 390 parts per million by volume, parts per million is essentially like a percentage, except with million instead of 100, right? So this would be, whereas 390% would be 390 divided by 100, this will be 390 divided by 10 to the 6 times, that's the portion of the gas, the gas that we're looking at that is CO2, times the pressure of the total system, which is 1 atmosphere. Okay, so with that, then we could solve for CO2, right? Then we would start taking a look at, okay, now we have this amount of CO2 added. So we've got CO2, that's going to react with water. That's not water. H2O. It's going to react and give us H2CO3. So that will be established as equilibrium. And in this, in this case, maybe it's more accurate to say, let's see. We know that this reaction, that CO2 dissolving, that's really the equilibrium reaction. Henry's law tells us how much of that water partitions into, how much of that CO2 partitions into the water. This one is kind of like anytime we need it, we just make that relationship. So I would consider this like whatever CO2 dissolved from the equilibrium we just talked about, we can treat it as if it's H2CO3. So let's not worry too much about that once we have some value in this open system there. Okay, then we know we have H2CO3 in equilibrium with bicarbonate. And a proton. And we also have equilibrium between bicarbonate and carbonate, but nothing else is in solution. So we don't think it should be super basic. And the only thing we've done so far has been adding CO2, which becomes H2CO3. And as soon as that becomes in equilibrium with anything, we're adding the proton. So immediately, we know that this is the only thing that's happened is we've added acidity, if anything. So then we can ignore the role of carbonate. There's going to be a very small amount of CO3 2 minus, but we can ignore it because we know that we don't have any way it could be basic, especially not very basic. Okay, so let's take a look. Just with this part alone, we could probably see how we could solve for that value, for that acidity, given if the other parts are known, or we can solve for them. let's take a look to see how the book does it. I guess I had two different slides. Okay, so it says we have a number of equations to work with based on these equilibriums, but we also need one other concept, and that's charge neutrality. So I'm going to revise what I said a moment ago when we were taking a look at this. I said we could probably try to solve for that. If we did try from here, we'd probably get stuck, now that I recall that. So as we'll see, this concept will talk about charge neutrality. A solution of water, or any solution really, cannot have more positive charges than negative charges. It's sort of a chemical or physical phenomena it's just an impossibility. We should always have an equal amount of negative as positive charge. That's this this thing that they're talking about. Okay, so the rainwater is assumed to have started without any electrical charge, and no net charge is added to it by the adsorption of carbon dioxide. So then, to maintain this charge neutrality, the total positive charge contributed by the H+ ions must equal the total negative charge from the bicarbonate, the carbonate, and hydroxyl ions. So anytime we have water, we're going to have some H+ and OH-. We know that because that's the equilibrium with water, right? That's the acid-base properties of water itself. So any amount of H+ that we added has to be counterbalanced by that HCO3 HCO3 2-, and OH-. So we can write another equation here based on that to say, well, we only had one source of plus, so the pluses are going to be equal to all the minuses. And we're going to do that in a charge equivalence manner. So it'll be 1 times HCO3- and 2 times CO3 2-, because it has a 2- charge. So we're talking about the molar equivalence of charge here. And that's where that molar equivalence we talked about earlier comes into play. Okay, and I'll just leave this highlighted just a little bit. Okay, and it describes that. Okay, so knowing that rainfall is likely to be slightly acidic, I explained that a moment ago. It's going to simplify, the book's going to simplify this and say, well, that bicarbonate is going to be really, really small, so we're just going to ignore it. Okay, so then we're left with H+ equals HCO3- plus OH-. And if you recall, we can actually get OH- in terms of H+, given that we know something about the equilibrium of water right here. Okay, so with that then we can probably work to solve it. I'm probably going to move these slides around a little bit so they make a little more sense, at least for next time. So the charge neutrality we wrote, bless you, as OH-. This H+ is going to be equal to that, plus the HCO3- plus 2 times the CO3 2-. We're going to say this goes to 0. And so we're left with that equation. We have the equilibrium equation over here. So we have that equation, we have this equation, and if we need it, we also have water, of course. And we know that the K for water, that's 10 to the minus 14. Okay, so that's kind of what we have charge neutrality gives us the second equation. We have this. Okay. Right, so now with all of that information, okay, I kind of see, sorry, a little, feel slightly out of order with these notes here. So with this, work on this for a moment. See where you could go from here to see if you could take the next steps. Bless you.
Given the KW of the carbonate series?
Yeah, so you would be given the, we can kind of take a look backwards a little bit, but yeah, we would normally be able to look that up, or you'd be given that. So the one that's relevant is 6.35. That's the pKa for that first reaction. All right, so my thinking on this is that we can take that water equation, substitute OH such that, or solve for OH so that we know that the amount of OH is 10 to the minus 14 divided by the H plus. Then we can substitute that into the charge neutrality equation so that we can get rid of the unknown of OH minus, get some form of HCO3 minus relating to the amount of H plus, and then we need to find some other equation to relate that HCO3 minus to the total that we have. And so that reminded me that, oh yeah, well, we should also consider another equation here that says the total CO2 that we have in the system, total carbonate, is going to be equal to the sum of the components, so H2CO3 and HCO3 minus. And we'll take that the carbonate is essentially zero in this particular case. So with that, I think we should be able to get there. Let's take a look at how the book is approaching it then. Okay, so then we take the water equation as we started with, substitute in, get the H plus equal to HCO3 minus plus the 10 to the minus 14th divided by H plus. Could rearrange that, but then here they're going to substitute in right here for, okay, so what they did here was they took that Ka1 that we were talking about a minute ago, should be 10 to the minus 6.35. That's for the equilibrium between H2CO3 with bicarbonate. HCO3 minus plus H plus. So when we set up that equation, it looks like this: H plus, HCO3 minus divided by H2CO3. Okay, so what they did then was they rearranged this to solve it for HCO3 minus and said that's going to be equal to this. I'll write it as K1 like they did. So when we solve for that, that should be K1 times H2CO3 divided by H plus. So this is what they substituted in right there. That gives us this K1 times, they wrote it as CO2 dissolved aqueous, so that's the same thing as writing H2CO3, plus this value, and we notice there's a common denominator, so they merged them both with H plus on the bottom there. Okay, and from here we can see that, well, we can multiply both sides by H plus and get H plus squared. To simplify that, then we get something in terms of the CO2 that we know something about. Okay, we didn't actually need the total CO2 equation that I was referring to. All right, so from here, they do exactly that, right? They say H plus squared, we have that, and we know that from our, we can solve for the CO2, which we didn't get the Henry's law constant. I showed you how that would work, but we didn't bother getting that number yet, so we'll see them get the number here. That's again from a lookup table, and so that's just some value that we'd be given or look up. But we do have that 390 times 10 to the minus 6, or divided by 10 to the 6, either way you want to look at it. That gives us some moles per liter. Okay, so then we can solve, and with all of that, we end up with the pH of natural rainwater being 5.62 as our answer. So slightly acidic. Does that make sense? It's kind of a long journey there, but that's a good encapsulation of the carbonate system, and can give us a good understanding of what's going on there. Yeah.
How did the bicarbonate turn into just carbon dioxide?
Yeah, that's a great question. So it didn't turn into it necessarily. What we did was we substituted it based on the known equilibrium. So we know there's some amount of bicarbonate given some amount of carbonate as a function of pH, right? That's this equation right here. We know this equilibrium equation shows us we have that equilibrium, and we have a definition. That's where the 10, you asked about that, right? That K for the 10 to the minus 6.5, 6.35. So we have this relationship, and we can define the bicarbonate in terms of the carbonic acid, the CO2. So really, we were just taking an algebraic substitution here. We had found H plus from the charge neutrality in terms of HCO3 minus and OH minus, which we substituted. So now at this point, we wanted to just substitute in, this goes to here, which then results in this portion. The other thing that they did here is we had basically two H pluses. It was this divided by H plus and this divided by H plus, and just merge the common denominator there. So with that, then we can just put it in terms of the ratio K1 and the CO2 that's dissolved. It's a good question. All right, any other questions or issues? All right, so good if I give this on an exam? Getting thumbs up here. I'm not sure if that's sarcastic or what. Okay. All right, so that's the carbonate system that will be playing a role in any of our alkalinity systems and relate to our hardness if indirectly. But really, both our alkalinity, our hardness, all of this, the carbonate system, they all end up interrelated on that charge neutrality principle, right? So the net charge of our system has to end up neutral. If you ever take a course that deals with aquatic chemistry, geochemistry kind of stuff, especially geochemistry, one of the things that you would do if, let's say, you're studying a river or something, you'll probably take measurements of all sorts of different ions in solution, especially the major ones, but then you also try to capture the smaller ones. And one of the tests to see how well you're doing in terms of taking your measurements and characterizing your system is how close did you get to a neutral charge at the end of the day when you add up all these measurements that you've taken. And so if you're ever involved in that kind of thing, that's actually a pretty big part of what's going on. Okay, so I guess I was a little ahead of myself in part of this, or maybe I should put this up front. What is hardness? That's that concentration of the multivalent cations, mostly calcium and magnesium. Technically, we'd include like iron and aluminum and things like that. But primarily what we're referring to is magnesium and calcium. Why might that be important in water distribution systems? Well, we see this pipe here on the right. We had, here's the metal pipe right here. And then we have layers and layers of calcium and magnesium deposits, right? So this mineralization that's happening there. And actually that's preferred. We prefer that to happen over the opposite, because typically, and as you might see if you think about the solubility things, solubility can go one way or the other. It's pretty rare that it just sits right at an equilibrium, right? You would typically be depositing things slowly or eroding things slowly based on the chemistry of your water. Could be rapid if you had some crazy chemistry going on, right? If you pour a bunch of really harsh acid over metals, sometimes that'll cause it to erode quite rapidly. So we tend to design our systems so that the pipes are not eroding. They're just going to, over time, constrict a bit. And over a very long time, that could become a problem and we'll have to replace them. But that's a better problem than them just breaking and leaking and having intrusion of groundwater into our water system. All right, so alkalinity, I mentioned this. It's a measure of water's ability to absorb acid with about no pH change. So it's kind of like a buffering capacity. If you have the carbonate system, if you have CO3 2 minus and you add in an H plus, you will end up with, obviously this is an equilibrium equation like we've been saying, but part of what happens is you get HCO3 minus, and what do you notice? Well, you didn't effectively add raw H plus to the system. At least this one molecule reacting, one CO3 2 minus reacting with one H plus yields one HCO3 minus, no net change at that level, at the scale of just that particular time. So if you have a lot of CO3 2 minus, there's a fair amount of buffer there that allows you to add acid without much pH change. So this is what happens when we're titrating something, right? We are adding a base or an acid, and for a while, it doesn't seem like we're going anywhere because there's some buffered system there. Eventually, we'll overcome it and get beyond it. So that's kind of the definition here of alkalinity. Okay, so then coming back to this concept of how we express it, when we talk about such and such alkalinity as CaCO3, we will also talk about hardness as CaCO3 for this similar reason, but it's more for the calcium in it. So again, they are quite related here. We need a term called equivalent weight. You've probably seen this before, probably used it before. We're just going to dive in a little specifically here to make sure we get this concept. So the equivalent weight will be the atomic or molecular weight divided by its charge, N. So if N is the ionic charge, or we could also look at it as the number of hydrogen atoms required to replace the cation. So in terms of CaCO3, Ca is 2 plus, CO3 is 2 minus, and if we wanted to replace the calcium with protons, we would need 2 to get H2CO3 molecule, right? So that N is equal to 2 for CaCO3, right? You could just look at it, oh, it's Ca2 plus, N is 2. But might be nice to just notice that H2CO3 is what we just spent half hour talking about, or an hour, and that now is coming back into this scenario. What happens, that substitution there, the fact that we have a calcium means we kind of have a 2 proton buffering capacity there if we had dissolved CaCO3. Okay, so that's the N. Now, what's the equivalent weight for CaCO3? Here's where we see that the math becomes a little handy. So calcium is 40 grams per mole, carbon is 12, and then we have 3 oxygens. And if we add all of that up, that's an even 100. So the molecular weight of CaCO3 just happens to be really convenient. Okay, so molecular weight CaCO3 is the most convenient molecule ever at exactly 100, or exact enough. So then if we divide that by 2 for the equivalent weight, then we have 50 grams per charge equivalent, or 50 milligrams per milli equivalent charge. So when we see the EQ, we should think equivalent charge. Well, really it's meaning equivalent, and we kind of assume that they're talking about charge there. Okay, so then MEQ is milli-equivalents of charge. So we can write that, the equivalent weight of CaCO3 as 50. If we were to just take calcium by itself, that's 40 divided by 2, it's approximately 20, right? So 20 milligrams per milliequivalent. Okay, so that's equivalent weight. That's the molecular weight or atomic weight divided by the charge. Then we can use that to convert from some sort of a milliequivalent of X. So when we talk about milliequivalents of CaCO3, this is kind of what we're talking about. So milliequivalents of X, and we'll convert it to milligrams in a moment. So milliequivalent would be magnesium to the equivalent milliequivalence of magnesium is to take the milligrams. Really all we're doing here is a molar conversion from mass to moles. Then moles to moles of charge. Moles of molecule to moles of charge. Okay, so if you understand that's the sequence of what we're doing here, hopefully that can kind of make more sense in your mind. These things are pretty straightforward, but easy to just kind of get lost on for a minute, you know, when you're like, wait, what are we doing exactly here? At least that's my experience, right? So try to keep this in mind. What we're doing here is just a molar, a change from mass to moles, which is why we take some milligrams divided by that molecular or atomic weight that's built into this equivalent weight thing. That lets us convert it right there. At the same time, since we also adapted for the charge, we are doing that second component. So if I were to, I'm going to just highlight this a little, hopefully make this a little clearer. So we have one thing happening here, and then a second thing happening here. And I'm going to say that this is number 1 and number 2, right? So all of that's happening in this exchange of using that equivalent weight. Okay, so then on top of that, we can describe, okay, milligrams per liter of, let's say, magnesium as CaCO3. When we write something like that, it sounds bizarre. Milligrams of liter as of this as that. That just sounds weird, right? It turns out because of the system and CaCO3 is so convenient, it turns out to be a pretty handy tool. So we could say milligrams per liter of magnesium, for example, 2+ as CaCO3. What we're going to do then is say that's going to be the concentration of magnesium in milligrams per liter. Just multiply it by 50 and divide that by the equivalent weight of our magnesium in this case. So we can convert anything, and the way to look at this is basically milligrams per liter of magnesium as if it were CaCO3. Okay, so that's kind of the mental note you can make. That's what we're explaining, so as if it was this particular scenario. Okay, does that make sense? It's all, like I said, pretty straightforward when you just do it, but the concepts can certainly get convoluted as you're, you know, trying to put it in action and you're forgetting a piece or something. All right, so just a quick look at some equivalent weights. You know, you could make sure that you're able to calculate these on your own. Might be a reasonable idea. Again, it's very straightforward, but we can see the atomic molecular weights, equivalent weights. So we just divide 1 by the charge, right? So aluminum is 27 grams per mole, charge is 3, so it's 9 milliequivalents per milligrams per milliequivalent. Okay, you can do grams per equivalent, but so often we're using milligrams per liter, we can just say milligrams per milliequivalent. Okay, a couple of the things down here, we can actually take a look at neutrals. So CaCO3 we've talked about, right? The thing itself is neutral, but it contains that calcium that has a 2+ charge. You'd have to take 2 protons to counteract that charge, right? So keep in mind that even though it doesn't look like there's something there, even just CO2, right? CO2, when you dissolve it, is going to be, we would describe it as 44 grams per mole, but then you're going to effectively have a 2 charge involved. Okay, so got some examples. I think I'm going to leave it off here, and we'll pick up here, get into hardness and some more of the softening next time. All right, and I'll plan to post a homework for you later today or tomorrow, and I think we've got a couple weeks for that. All right, so I'll see you guys on Thursday.